wedge dt. And we don't have to worry about the time derivatives on that term because we're wedging with dt. I learned my lesson. All right. But, okay, great. The question, though, we're looking for is how to formulate the other two Maxwell's equations, right? Okay, so yeah, what's this? This is like my rho, right? And, for convenience, we're putting epsilon naught equal to mu naught equal to 1, if you guys don't mind. Yeah. I mean, why not? You know, whatever. Let's see here. So we have plus the flux form of, good grief, partial E, partial T, minus the curl of B, I guess, at the moment, wedge dt. So that's, all right. So notice this equation, if we put them both to 1, this becomes like partial E, partial T, minus the curl of B is equal to what? Minus J, right? So I can use that over here, plus like phi of, what'd I say, minus J, yeah? Wedge dt. Pull the minus out. Right? And that, my friends, is the Hodge dual of the current one form. So what I'm telling you is that, Daniel, go back over here. If we take these two equations, right? We can take these two equations and we can trade them for the exterior derivative of the Hodge dual of F is equal to the Hodge dual of the forecurrent. This is the other two Maxwell's equations. Conservation of charge is then immediate because the exterior derivative of the Hodge dual of J is the exterior derivative of the Hodge dual of the Faraday tensor, which, by the way, is 0. So yay, charge is conserved, which is nice. Now, if you look in my notes, the way I have derived these things, all these calculations are from a previous time when I, before I really embraced. So I have, over the years, grown more and more conversant in the work and the flux form calculations, and that allows me to circumvent repeated index calculations. But if you look in my notes, the repeated index calculations are still there in all their glory. And, well, let's look. I take your no thanks and trade you you're welcome. And glad you asked. All right. Well, why is it over there? Oh, it's weird. If I do that, it's okay. It's fine. So, like, look at this. For instance, you know. I don't know. Man, where'd my laser go? So I personally found this very exciting as an undergraduate because I just thought it was really neat that you can rewrite 4 of Maxwell's equations simply as 2 tensorial equations like this. But when and like here's my calculation of dA in the notes. It's similar to what we did, but so here's again we did this calculation a second ago. So in summary, dF equal to 0 is Faraday's equation and no magnetic monopoles, and this equation is Ampere's law with Maxwell's correction and Gauss's law. Now, if you look at Griffith's electromagnetism, well, you guys aren't, so let's skip that, right? But you can introduce something called the co-derivative. You have a homework problem on that. The co-derivative is built from Hodge duality and the exterior derivative. And what it does is it gives you a way of differentiating a p form and getting a p+1 form. So the way it works is like you Hodge dual, you take the exterior derivative, that lowers the derivative by 1, the order by 1, and then you Hodge dual again, and it takes you back to +1. So it's like, anyway. There it is. This is the co-derivative. Hodge dual, differentiate, Hodge dual again. Yeah. I'm missing an apostrophe. If you listen very carefully, you can hear the sound. Me not caring, but sorry. Sorry, I should behave. Thank you for pointing out my grievous grammatical errors. There are many. There is a larger question to answer here, which is, what does this whole study get us? Well, one of the things it gets us is a clear path towards proving the proper coordinate change properties of Maxwell's equations with respect to special relativity. So one of the reasons that we have special relativity, which is the study of space and time subject to Einstein's axioms and all that, is because electromagnetism itself was inconsistent with classical mechanics, but in fact already relativistic. In other words, if I write down Maxwell's equations in one frame of reference, and if I look at another frame of reference as defined by Einstein's special relativity, an inertial frame of reference in the sense of Lorentz transformations, the form of the equation stays the same. So basically, you can prove that if you have that the 4 potential is actually a 4 vector. In other words, it transforms as a vector. And of course, we know the chain rule for the partial derivatives like that. If that's the case, then this Faraday tensor is automatically a 2 tensor because it's built with tensors. And like I have the calculation here. If I changed coordinates to the barred coordinate system, I take barred derivatives of the barred 4 potential, and lo and behold, I get 2 coordinate change matrices that are just the right kind to be the coordinate change. This is the desired coordinate change formula for a 2 tensor. You guys maybe understand that a little bit in here with the homework, like 3 homeworks ago, something like that. I'm ignoring that, a certain head shaking. But anyway, indeed, the Faraday tensor is a tensor, meaning that it transforms as it ought to. And likewise, the 4 current is in fact a 4 vector. Now, I asked Dr. Kafitz, my general relativity instructor, why is it that the 4 potential is a 4 vector? See, if you really understand the underlying physics of that, like, there's a question you should ask, which is, how do you find the potential? How do you find the voltage function? And how do you find the current density? In other words, how do you derive V and A vector in a physical situation? Do you guys know what the answer to that is? Well, the answer is you have to be given the charge density and the current density. Like, charge and current density are physical, they're observed, right? I give you those, you can use those and do certain integrations, and through those integrals you derive the voltage and the vector potential, right? So to prove that the vector potential has the appropriate coordinate change properties, really it obligates you to study coordinate change on those integrals. I've never seen anyone do that in the class. I asked Dr. Kafitz if it had been done, and he was like, he wasn't understanding my question for a little bit, but after a little bit he was like, oh yeah, that was all done in the 50s. It's in papers. I've never seen these papers, but allegedly it's been done. So I hope it worked out. Otherwise, this is all a house of cards. But anyway, so last thing today, since I started late, I'm sorry, my fault, but I wanted to talk to you guys about electrostatics in 5 dimensions. So we just set up electromagnetism in 3 spatial plus 1 time dimension. Imagine that you wanted to talk about physics in 1 time plus 4 spatial dimensions, right? If you were to do that, it's as simple as making your 1 form potential now depend on not 1 and 2 and 3, but now 4 components. So your A would look like this, and of course, that gives us this, this 1 form potential. This is a sum from 1 equals sum over 1 to 4. And then, of course, you would probably want to work with Minkowski 5-dimensional spacetime. Looks like that. And then your 2-day, your Faraday tensor would still be. Why is the quotation mark backwards? It's LaTeX. I'm too lazy to do it properly. So dA would be the exterior derivative of this 1 form, and it would give you a 2 form in 5 dimensions. How many components are there in a 2 form in 5 dimensions? That question is 2. What, 5 choose 2?
Probably.
What's 5 choose 2? It's more than 8. I'll tell you that. All right. It turns out that gives you that gives us, well, anyway, we have a 5 by 5 antisymmetric tensor. Jaden, you should know. 5 by 5 antisymmetric tensor. How many components we got? N squared minus n over 2. What we got? 25 minus 5, 20 divided by 2. I think this gives us 10 components. All right. I think 10 components. And so if we have 4 of those are the electric field, right? That leaves us 6 components left over for the magnetic field. So if you're talking about electromagnetism in 5 dimensions, all of a sudden there's not this duality between electric and magnetic fields. There's an electric field and there's what's called a magnetic flux. It's no longer a vector field. It has to be thought of as a differential form. This is the nature of higher dimensions. This is part of why string theorists have to work with differential forms in order to understand things in higher dimensions. It's just the formalism that you need. Anyway, so here is what the Faraday tensor in a 5-dimensional context would look like, something like this. We have a 4-dimensional electric field. We could still think of that. But the magnetic field has actually like 6 components. I'm not sure exactly how to think of that. More compactly, we've got the Faraday tensor is E wedge dt plus B. Okay, so the most famous problem in electrostatics is you just have a single point charge at the origin, nothing else, right? And what happens? The Coulomb field spreads out, right? If you guys have had Physics 232, it's like Q over 4 pi epsilon naught, and then 1 over r squared, right? The inverse square law. If you've had Physics 1, you've studied the gravity, like GMM over r squared. That's the inverse square law. This is what happens when you have a spherically symmetric force in 3 dimensions, right? So the question that I'm begging here is, well, how does that work in 4 dimensions? So we can calculate that if we assume that we have a single point charge at the origin, all right? And that's what I'm going to do. I'm going to say, okay, so the inhomogeneous equations still have this form. It's just that now I've got a charge density and we've got more currents to think about, but we'll just focus on the question of a single point charge. In that case, we just have rho dt to worry about. And so Maxwell's equations, the stereo derivative of the Hodge dual of E wedge dt would be equal to 1 over epsilon naught rho like this. This is Gauss's equation in the 4-dimensional context. And then what I'll do is I'll integrate over a 3-sphere in 4 dimensions. really a four-dimensional ball with a three-dimensional edge. And we can use generalized spherical coordinates to do that. So what you do is you just add another angle, like psi, that ranges from 0 to pi, just like we added, theta here. So these are physics. The theta and the phi are flippity-floppited, as you can maybe see. But anyway, the volume, here's something you should fuss about me. I really should say that the 4 volume and the surface volume of a 3-sphere are this. So the volume of the 3-sphere is pi squared r to the 4th over 2. And the area is actually, you differentiate this, you get that, 2 pi squared r cubed. And if I wanted to have a point charge with like uniform smeared out, I would just give this formula. So like it's got 2q, basically q divided by the volume of the 4-sphere from 0 to a, and then 0 outside. And then if I integrate this over that 4-sphere, I'm integrating that. So this integral works out to the charge over epsilon naught. How does this integral work out? Well, because of the spherical symmetry here, this has to integrate to the, this was, what's this? Going from here to here, that's Stokes' theorem, generalized Stokes' theorem. Integral over m, integral over boundary of m. Notice that the exterior derivative is gone. Now I just have this, and if you reason through it, that should be equal to the magnitude of the electric field times the surface volume, if we reason through this integration. Which then, if we solve for this, we get the electric field as q over 2 pi squared r cubed epsilon naught. In other words, if we have an electric field which spreads out in 4 spatial dimensions rather than 3, it drops off as the cube of the distance from the charge rather than the square of the distance from the charge. This is actually not surprising. If you had physics 2, the line charge is essentially the 2-dimensional situation. If you have a line charge, the electric field drops off as the reciprocal of the distance from the line charge. Because essentially in 2 dimensions, if your flux spreads out in 2 dimensions, it drops off like the reciprocal. If it spreads out in 3 dimensions, the magnitude of a symmetric field drops off as a square. In 4 dimensions, it drops off as a cube. In 5 dimensions, it would drop off as a fourth. And this is one of the reasons that string theorists think that, well, they have various scenarios that, like one of the popular things when I wrote these notes was so-called brain world scenarios, where the idea is that gravity is able to spread out in like all of the dimensions, whereas the standard model fields are stuck on these branes. And because they're stuck on the branes, the standard model fields have to just spread out in 4 dimensions, whereas gravity is free to spread out in like 10 dimensions. And that's why gravity is so weak in comparison. Like if you study physics, the weak, the strong, and the electric fields are way, way stronger than gravity. Why is gravity so weak? String theorists say because there's these 6 extra dimensions you can't see where gravity spreads out in. At least that's what they said when I wrote these notes, but that was 15 years ago, so who knows what they're saying now? Who knows? I don't. But anyway, I think this is maybe a good illustration of the kind of thinking you can do with differential forms. You can generalize equations to many dimensions, and I think it's fun. I don't know. You can disagree with me. One of the things I'm missing, though, is a proper discussion of magnetic monopoles in here. I thought I had a homework problem for you guys, but I don't think I did. I'm kind of annoyed. Anyway, thanks, guys.